All right, so I am now recording the webinar as we move forward, and then we will get to the presentation. But prior to starting the actual presentation, I do want to, where did there we go. Sorry, I'm a little bit out of sync here. There we go. For those of you who have logged in both on mobile and the computer, there is a handout section, and you can download the handouts at any time during the webinar. The handouts for this particular webinar include a printout of the slides that we're going to go through, as well as a copy of Health Canada's guideline for naturally occurring radioactive materials for Canadians. So we'll refer to that document in the presentation, and this is an easy way for you to get a copy of it. Alternatively, that's also available on Health Canada's website. At the end of the webinar, we will save the recording, and at some future date, it might take us about a week, we plan to add the webinar available to our website, and all participants will get a link to access the webinar should you want to go back and review any part of it. Okay, we would like to start off with asking a few questions about you, get some information, and the webinar has a polling feature, so I will put a poll up on the screen and ask you to answer to the best of your ability. And the first poll that we're going to start with is where you are located. So we're curious as to where across the country people are located, so if you would, s'il vous plaît, fill in the most appropriate item for you, that would be appreciated. And we'll just give everybody a few moments. That's great. I think everybody's pretty much done now. Those who have access, some may not be able to access their poll part. So it looks like most people who are attending are in Central Canada. Let's see if I can share the results with you. There we go. Yeah, so most people, it looks like, are in Ontario or Quebec. There's a few of you from the West Coast, and then there's a few actually not in Canada. So welcome to Canada via our webinar. Thank you for joining us. Okay, the next webinar that I wanted to go through today was to ask you about how you had heard about our webinar. So if you could let us know, did you hear about it through our social media channels, from our emails, somebody else recommended it, or how else did you hear? Well, that's good. We've got people who have heard of this webinar through a couple of different ways, so that's great. All right, I'll close the poll now and share the results. Most of you got an email from us. Some of you were recommended by friends. I think social media and other options were also the main ways to get in. So that's great. And the last one, I'm just curious as to what industry you were working in. I only gave 4 choices here. I wasn't quite sure what to put in. So fish and aquaculture, fresh or wastewater processing, mining, other. All right, lots of you are coming from other. Good to know. Few from mining, some from fish and aquaculture. That's awesome. Great, so we'll share the results from that. Is it working? Share. There we go. So by and far, the other category, which does encompass a lot, was most people. So apologies that I couldn't figure out what else to put in the 5 choices I'm allowed to put up on the screen. But we've got a good idea of where we're at now, so that's great. All right, well, we will move on now into the presentation. So I will turn off the webinar now and hook up my other microphone, and then we'll move on to the actual presentation. All right, my secondary microphone is connected. which I have heard has given us better sound quality, so we will go with that for the presentation today. All right, so our webinar today is going to talk about radon, and we're going to focus on radon in high water use facilities. So the reason that we're doing this webinar is really it's to provide an introduction to the hazards of radon gas in facilities which utilize a high volume of water. Radon does exist all over the world, and it can be an issue in other areas. Mining is one, but some of the issues that you'll find in mining and high water use facilities may be a little bit different. So this webinar is to focus on high water use facilities. Some of it can be transferred to other facilities. If you have any other questions for other areas, please don't hesitate to give us a call after the fact. Right, so we're going to talk in this webinar, I'm going to talk about what radon is. So I'll introduce radon, what it is, what are its potential health hazards, why are we concerned. We will cover a little bit about how radon actually gets into our workplace air, focusing on the water issue as well as other ways. We'll talk briefly about how we would go about measuring what radon levels we have. I'll talk about some of the radon radiation protection guidelines and regulations that exist in Canada, and then we'll briefly discuss some measures to reduce radon exposure. Now, our webinar is intended to be an hour in length, including questions, so we won't necessarily be able to cover all topics in excessive detail, but that's an introduction, and then if you need any assistance later, we're certainly to help. All right. So what is radon? Radon is an odorless, colorless radioactive gas that is formed naturally by the breakdown of uranium in soil, rock, and water. Now, uranium exists in some quantities everywhere in the world, and therefore radon exists everywhere in the world as well. Radon gas itself is an alpha emitter. It emits an alpha particle as its radioactive decay. It has a half-life of 3.8 days, meaning it's quite short-lived. So after 3.8 days, half of the radon that you had is gone, has decayed into its daughter products. And that would be great if we only had one source of radon and we never got any more, but radon is constantly being created in the Earth's atmosphere and it replenishes itself. So we do get radon potentially building up in spaces, and even with the half-life, we can have some high quantities. Radon is an inert gas. It is not chemically reactive, which can make it a little bit more difficult to deal with when we want to trap it or get rid of it. And of importance for high water use facilities, radon is water soluble. So I like to say it hitches a ride with water. It can get into our buildings and workplaces through the water that we use. Radon is somewhat more dense than air, although not significantly. We don't see that it's going to settle out completely to the bottom of facilities and things like that. It's certainly not going to move air out so that you have a lack of oxygen. It mixes fairly well, and it does definitely accumulate in enclosed spaces. So when we talk about radon, we also have to introduce the concept of radon progeny or radon daughters. So radon daughters are the radioactive elements that are created when radon gas decays. And when we're looking at the health effects of radon, we really are looking at the short-lived radon progeny or daughters. So these are metals that are created when radon decays, and daughters in turn decay into other things. They are solids, and they are radioactive in and of themselves. These solid particles tend to attach to our dust particles in the environment, and so that when we inhale them, oftentimes they can stay in our lungs. And two of the radioactive daughters from radon gas are actually high energy alpha emitters. And as such, they and radon are giving off alpha energy. So here is a slide that shows pictorially radon gas and then its short-lived radon daughters or radon progeny. And there we So the alpha particles you'll see there, those are the alpha particles that are emitted that are sort of moving off to the left of the screen, right of the screen, depending on which way you're looking at it. So this pictorially shows us where radon gas is, what its short-lived radon progeny are, and which ones are emitting alpha particles during their decay. So one of the reasons we're concerned about radon is that it is radioactive. And when radiation interacts with the body, it can deposit that energy into the body. And that was what we call a dose. So the transfer of energy from the radiation emitted by the radioactive material transfers energy to our tissues, and that we call a dose. And that energy that's transferred may cause damage. So radon in particular, we mentioned that radon progenies attach to the dust particles in the air, and when we breathe in that air, the radioactive aerosols enters our lungs. Radon gas, we can breathe it in, but because it's non-reactive, we tend to breathe it right back out again. Very little of the decay that occurs from radon gas itself occurs within our lungs. For our health effects, we're really mostly concerned with the progeny. So when we breathe in air, the dust particles can stay in our lungs, and if they have radon progeny on them, as the progeny decays, they emit their alpha radiation, and that transfers energy to the cells in our lungs. And this can cause damage to the lung cells. There are no immediate symptoms when we have one cell that's damaged and changed. We really can't tell right away. We have to wait. But that damage could include a mutation that might lead to cancer. So by having the radon progeny breathed into our lung and emitting the radioactive decay products or alphas, we may have cell damage that leads to an increased risk of developing lung cancer. The development of lung cancer because of radon and radon daughter exposure, it's not guaranteed. It's probabilistic, meaning that it follows a probability curve. There's a chance that you will get it, and there's a chance that you won't. So in fact, not everybody who is exposed to elevated levels of radon will develop lung cancer. At the moment, the research cannot show us whether there is or is not a threshold below which exposure presents no risk. That sort of research is quite difficult when we're looking at very low doses and we need lots of subjects in the study. And so we haven't gotten to the point yet where we can say for sure whether there is or is not a threshold. So for the sake of caution, we assume that there's no lower threshold below which the exposure presents no risk. And this means that the more dose that a person receives because of radon exposure, the higher their risk of developing lung cancer. And the risk of lung cancer from radon is going to depend on a few things, including how much radon is in your workplace and home, how much time is spent in these areas, and whether or not the person who is exposed to radon is a smoker or has ever smoked. In fact, the combination of smoking and radon results in a larger exposure or larger risk than the individual risks added together. So if the risk from smoking was A, the risk from radon was B, the risk from the two in combination is more than A plus B. So there's some sort of synergistic effects that go on where having radon and smoking does increase the risk beyond the individual things themselves, individual exposures themselves. All right, so when we are measuring radon, we want to talk about how much radon is present to figure out what our risks are. We're typically going to measure radon gas because it's easier than measuring the radon progeny. And when we measure radon gas, we're going to measure it as an activity concentration, so how many becquerels in a cubic meters of air. And a becquerel is a scientific unit that indicates how many decays are occurring per second. So if we had 200 becquerels per cubic meter, we would have 200 decays of radon gas in that cubic meter of air per second. Now, when we measure radon gas, we have to either know or assume the relative amounts of radon gas and its radioactive progeny to convert that to a dose, or a dose to a person, and therefore their risk. Now, according to the Canadian Norm Guidelines document, It gives us an easy conversion factor. It says if we were exposed to 200 becquerels per cubic meter for 2,000 hours, which is considered a typical working year, that would result in a dose of 1.4 millisieverts. Radon progeny, on the other hand, is traditionally measured in working levels, which is a measure of its concentration. If we're exposed to 1 working level of radon progeny for 170 hours, which is approximately what you would expect to be exposed to in a month, that will result in what we call a working level month, 1 working level month exposure, which is equivalent to 5 millisieverts of dose to the person. So those are some numbers that we use when we're measuring and doing our dose conversions. All right, so we know what radon is now. We know that we can measure it and the units we're going to measure it in. How do we end up with radon in our workplaces? So radon can enter the building in a couple of different ways. We can have it come into the building from the soil, where the building is in contact with the soil, and we can have radon come into the building through the water that we use. So where the building is in contact with the soil, wherever there's a crack in the slab or walls, if we have gaps at the floor wall joints, openings around utility penetrations, floor drains with no taps, sump pits that don't have a good tight sealed cover, that can allow the radon gas that ends up in our soil from the decay of uranium to move into our building. In addition to that, we can also have radon emitted from water. So remember, radon is soluble in water. It likes to hitch a ride. And if that water comes into our facility bearing radon, that radon then can then come out of the water into our air. And this is particularly important to consider when we're using groundwater or well water. We don't see as much radon in surface water like streams and rivers, but certainly you can have higher concentrations of radon in ground and well water. We also can have radon enter buildings through the use of natural gas. Generally speaking, where natural gas is used, it's well ventilated, so radon has a hard time getting into our workplace breathing air, but it's also a potential for the way that radon can come in. Now, to focus on water, radon emission from water. So when the radon flows through rock and soil that has uranium in it, the radon that is created there can be picked up into the water and move along with the water into the facility where we're using the water. And once that radon is in the water in the facility, it can escape the water into the air of the facility. In particular, we're going to see more radon coming out of the water into the air when that water is agitated in the presence of air. So if we have water that is splashing, spraying, that sort of thing, radon is going to come out of the water much faster than if the water was simply sitting in a stationary state in a bucket or in a tank, sort of thing. And how easily radon transfers into the air is going to depend on the temperature of both the air and the water and the level of agitation. In dwellings, even if we have elevated water levels of radon, we typically don't use that much water in homes with our showering and dishwashing. So even 100 becquerels per liter increase of radon in the water only results in about an increase of 10 or so becquerels per cubic meter in air. But dwellings only use a very small amount of water, perhaps 1,000 liters a day. When we look at larger water use facilities that are using millions of liters per day, then even if you have a small radon concentration in the water, you may have a very good source of radon coming into the building through the water. So facilities that use large amounts of groundwater, well water, or water that's on the surface that's collected fairly soon after it comes out of the water may end up with significantly higher radon concentrations in their facility because of the radon that's coming out of the water that they're using. And this can include fish culture, water treatment facilities, etc., that sort of thing. Once the radon gets into our building, radon concentration indoors is affected by a few things. So it's affected by our source of radon, so how much uranium is in the soil and in our building materials, and the soil characteristics, so how well that radon can travel to get to our building. It's going to depend on the concentration of radon in the water and how much water is used and how much it's agitated. It can depend on our heating, ventilation, and air conditioning systems. The more ventilation we have, the more fresh air we're adding and the more radon we're taking out. And the heating and air conditioning will affect the temperature of the air, which will affect how well the radon can get into the air from the water. And our occupancy patterns may have an effect too. In the summer, when we have our doors and windows open, we may have more fresh air coming in to dilute the radon concentration than in the winter when those are closed. Radon concentration indoors is also affected by our external environmental conditions. So our outdoor temperature, the barometric pressure, precipitation, humidity, and wind speed all can play a part in how radon concentrations, what the radon concentrations exist in the building. And what we'll see over time, if we're monitoring radon daily over time, we're going to potentially see a significant change in radon concentration over time as these things change. So as our barometric pressure goes up and down, as we get windy or more windy or less windy, if our humidity goes up and down, this will all affect the amount of radon that is present inside. And therefore we have to be careful when we're monitoring that we don't accidentally measure at a high point or accidentally measure at a low point if we do a short-term test. We want to measure over time and get the average. So if we're going to measure, what are we going to do? Well, to measure radon, there's actually two things we can do. We can measure the radon progeny, which would make sense because the radon progeny is actually what's really causing the dose to people. Radon gas itself, remember, we breathe in, most of it we breathe back out again. It's the progeny that causes most of the dose and therefore the issue. However, radon progeny can be quite short-lived and therefore can be rather complicated to measure. The typical thing is therefore to measure the radon gas concentration. It's actually much easier to detect. It's not that expensive to do. You don't have to be a physicist who knows how to use some complicated equipment to measure radon gas. However, we are measuring the gas and not the progeny, which is causing the dose. So we have to then make an assumption about how much radon progeny is present versus the radon gas that we're measuring, so how close in equilibrium they are. We call it the equilibrium factor. We make that assumption in order to take our radon gas measurement and convert that to a dose or what the risk for people exposed to that level would be. Radon gas can actually be measured in many ways. There's short-term tests that can be done, which include grab samples and using charcoal canisters. These are generally not recommended because they're measuring radon concentration over a short period of time. Even if you're using a charcoal canister and you're deploying it for a week or two, most of what that charcoal canister is measuring is the radon concentration over the last day or so. And because the short-term radon gas concentrations are very variable with our weather and things like that, they can vary by a factor of 3 to 5. So if we're only measuring in a very short time frame, we may be measuring at an artificially low point, we may be measuring at an artificially high point. We're not getting a good measurement of the average. It's kind of like measuring temperature. If I was to measure the temperature first thing in the morning, it's not necessarily a good indication of what the average temperature over the week was. Same as if I had measured temperature at 5 o'clock in the afternoon, when it's really hot that day, it's again not a good indication of the average temperature. So if I want to get an average indication, I need to be measuring over time. And that's why long-term tests are recommended. And there's two types that are typically used, an electret monitor or an alpha track monitor. And those have different technology inside, but they work according to a fairly basic, a similar premise. They're generally speaking a plastic canister with a filter on the outside. The filter will allow radon gas and air into the detector, but it keeps the radon progeny out. And then when the radon decays inside the chamber, inside the plastic canister, it interacts with the detector. And then you would send that off to the laboratory. So I'll talk a little bit more about long-term tests in the next slide. Continuous monitors can also be a good option, but depending on the type that you get and what you need, they can be expensive. If you want to use them long-term, they need to be calibrated on a regular basis. So you're going to need to be sending them off for calibration at least once a year to make sure that they are still reading accurate levels. And depending on how the continuous monitor works, you need to understand how it's calculating what it's giving you to display. Most of them on the market that are reasonably inexpensive will display a number on the screen, but that number is actually not very accurate until you've had a week of exposure. So a lot of the continuous monitors that we get are not going to help us measure daily or instantaneous concentrations. We're going to need quite expensive ones for that. So the recommended less expensive monitors are the long-term monitors, and these includes the electret monitor or the AlphaTrack. Same concept, slightly different detectors. So when you're deploying a long-term monitor, you would typically deploy it for 3 to 12 months. If we are expecting elevated radon levels, we may work on the shorter time frame and possibly down to 1 month, depending on it, because we don't want to overexpose our detector. These typically don't require power. It's a standalone passive device that we would open, put out in the time frame that we need, and then we would package it up and send it away to a lab for analysis. These give a very good indication of the average concentration of radon during the exposure time frame, and they're relatively inexpensive. They can range anywhere from $25, $30 to $50 if you're buying the test by themselves. If you're hiring somebody to put them in place, they may charge $200 or $300 for that. Compared to a $4,000 or $5,000 or $10,000 instrument, they're actually quite inexpensive. And this is the type of test that Health Canada recommends that people use to analyze and measure radon in the workplace and in homes in Canada. So once we've measured our radon, what do we do? How do we know what we have to do with our levels? And I'm going to talk briefly about our regulation of radon in workplaces. So there's two regulations that we generally look at. There's the federal regulations, and then there's the provincial regulations. So the federally regulated workplaces, those that fall under the Canada Labour Code, there are specific numbers in the Canada Labour Code with respect to radon that need to be maintained. Also, there are workplaces that are regulated under the Nuclear Safety and Control Act that's managed by the Canadian Nuclear Safety Commission. This includes uranium mines, nuclear power, people with radiation sources, that sort of thing. If you have that sort of work, then the radiation protection regulations require that persons in those work who are exposed to radon have their dose from radon monitored and reported. Most people, however, don't fall under the federal regulations. Most fall under provincial rules. Their workplaces under the provincial regulations. And therefore, where the regulations fit in is under the occupational health and safety regulations of the province or territory. I shouldn't just say provincial. Territory is the same sort of thing. The occupational health and safety regulation for that jurisdiction. Depending on the province or territory, there may be different or additive requirements under mine safety regulations as well. Because this is a 1-hour webinar, we don't have time to go through all of the provinces, but I can give you a quick example with Ontario. So for example, under Ontario's Occupational Health and Safety Act, the employer has a duty to protect the health and safety of the employee for the hazards that may exist. They're to take every reasonable precaution in the circumstances for the protection of the worker. The regulation is certainly not explicit on what you would do for radon or for other naturally occurring radioactive materials. And in this case, the Ontario Ministry of Labour staff have indicated that they expect employers to follow the safety measures documented in Health Canada's Canadian Guidelines for the Management of Naturally Occurring Radioactive Material, which I tend to short form in presentation and discussions as Canada's Norm Guidelines document. And that is attached as a handout in this presentation, and it's also available from Health Canada's website. So Ontario Ministry of Labour, it's on their website that if you have naturally occurring radioactive material present, they expect employers to follow the safety measurements documented in this document, and by doing so, they're therefore showing compliance with reasonable precautions for protecting the worker. So what's in the Canadian Norm Guidelines? Well, first of all, the Canadian Norm Guideline recommends that all workplaces be assessed for radon concentration since it can vary significantly. And that's words I've taken right out of the document and put in quotes there. Radon concentration can vary significantly in one type of business and from business to business. So they recommend that all workplaces be assessed. The Canadian Norm Guidelines also provides occupational dose limits for exposure to radon in workplaces that are not the ones that are federally regulated, so not including uranium mines. But other mines that are not federally regulated are fish culture stations or water treatment plants. In Ontario, it's expected that these levels of the Canadian Norm Guidelines will be followed. And the limits for dose due to exposure to radon and other naturally radioactive material is based on worker type. And this document defines 3 types of workers: the occupationally exposed workers, incidentally exposed workers, and members of the public. And it defines different limits for each group. These limits are consistent with the recommendations of the International Commission on Radiation Protection overall for radiation protection, and they're also consistent with the Canadian federal regulation limits on radioactive material exposure. The Canadian Norm Guidelines also provides us with easy-to-use dose conversion factors based on measured radon or radon progeny concentration. So if we do go to the workplace and we measure a level, we can use their dose conversion factors to estimate what the doses to our workers are, with the assumptions that we had in place on equilibrium. And it also provides classifications for the facility based on radon concentration. So, and we'll go over those in the next slide. Basically what it does is it says, based on your radon concentration that you measure, here's the classification that your facility falls into. And therefore, these are the actions that you need to take to protect the worker. So within the Canadian Norm Guidelines, there are 3 classifications for radon. If concentrations are measured, the average, and when we're talking about concentrations here, we're talking about your average annual concentration. So the typical concentration that you're going to see in the facility over the year. If your average annual concentration is less than 200 becquerels per cubic meter, the classification is unrestricted, and there are no further precautions needed to be put into place. In the range from 200 becquerel per cubic meter to 800 becquerel per cubic meter, this is called the Norm Management Classification. And the Canadian Norm Guidelines suggests the application of a LARA program, which means a way to keep doses as low as reasonably achievable. And that could include changes in work practices, changes to work procedures, introducing access controls for our areas and things like that. It also indicates that whenever possible, we should reduce radon levels to below 200 becquerels per cubic meter. So technically that should be done first. Do what we can to reduce our radon levels to below 200. If we're successful, we get all of our radon levels to a long-term average below 200. Now we're in the unrestricted category and we don't have to do anything else. If we can't, at least we've reduced them as much as we could, and now we're going to put in changes in work practices. Maybe we're going to spray water less. We're going to have different limited time in certain areas, things like that. If our long-term average concentration is above 800 becquerels per cubic meter, again, the first thing to do is to do what we can to reduce the radon concentrations to below 200. If we cannot do that, then what we need to do is put into place a formal radiation protection management program. This is the Radiation Protection Management Classification. So we're going to document our radiation protection program. We're going to introduce dosimetry for workers and, as necessary, provide protective equipment. And the intent of that is to keep workers' doses below the limits. We may now classify our workers, that sort of thing. The dose limits for workers under the Canadian Norm Guidelines are here. So for members of the public and incidentally exposed workers, in any 1 year, they're only allowed an annual effective dose of 1 millisievert. There's a bit of a discontinuity here because if you recall on the previous page, I'll go back, if we have an exposure of 200 becquerel per cubic meter, the annual dose from that is actually calculated at 1.4 millisieverts, but you didn't have to do anything more. However, when we're getting to the point where we're comparing to dose limits, the limit is actually 1 millisievert, not 1.4. So there's a bit of a disconnect there that occurred when they streamlined the document to align with Health Canada's recommendations in homes, and they haven't sorted that out yet. For people who are designated as an occupationally exposed worker, and there's a process to do that whereby people understand that they're being exposed to radon above the levels of members of the public. Once they're designated or assigned that category and they're aware of it, then their limit is much higher. It's up to 50 millisieverts in any 1 year, so long as it doesn't exceed 100 millisieverts over a 5-year period. Pregnant occupationally exposed workers, the limit is 4 millisieverts for the balance of the pregnancy. So once pregnancy is declared, from then on until the pregnancy is finished. It's unclear as to exactly whether or not this should apply to radon, because radon dose really is only to the lungs. It's not necessarily going to affect the growing fetus. So I'm not quite sure how, for example, the Ministry of Labor would interpret that for radon versus other radioactive materials. Keep in mind these limits are for all naturally occurring radioactive materials, not just for radon. So when we look at radon in water, in fact, there's very little health risk to us from ingesting radon or drinking radon-contaminated drinking water. Really, our concern from water is the radon that comes into the air, becomes radon progeny, and then we drink that. We breathe that. That's where most of the risk from radon exists. So Canada actually does not have guidelines for radon concentrations in drinking water. It's not considered a high risk. We're really only concerned with what happens when the radon comes out of the water and into the air. Additionally, there are no Canadian regulations governing radon levels in dwellings. And we have to keep in mind that if we're exposed at work and at home, then we have a higher exposure than if we were exposed only at one or the other. Just so you're aware, Health Canada does have a guideline that suggests that radon concentrations should not exceed 200 becquerels per cubic meter. So this is the same number now as in the Canadian norm guidelines for workplaces to be in the unrestricted category. And Health Canada recommends that in homes, remedial measures be taken if concentration is above that, then to reduce the concentration as far below that as possible. And they provide some guidelines on time frame. So if it's between 200 and 600 becquerels per cubic meter, they suggest that those measures be taken within 2 years to reduce the concentration, and that at higher levels that are above 600, that those remediation methods be done within 1 year. So those are the guidelines with respect to dwellings. They also say you should aim to reduce your radon to as low as you can, not just say, hey, I'm going to get it just below 200 and then I'm good. The lower you bring it down, the less your risk. Also, the construction of new dwellings is recommended that those should employ techniques that will minimize radon entry from the ground into the home. There's not a whole lot that can be done if there's lots of water in that home area that's high radon. But when we're building homes, Health Canada suggests that they should be built so that we minimize radon entry and then make remediation easy afterwards if possible. So what do we do to control our radon hazards? So we've done a measurement, we find we have elevated radon levels, we want to reduce our radon levels in our workplace. What do we do to control that? Well, the first thing we would look at is try to prevent radon entry into the building. So if we have a potential that radon is coming in from the soil gas in the soil around our building, we could find and seal any entrance points, particularly things like sump pumps, utility penetrations, that sort of thing. You can look at maintaining a positive air pressure in the building versus the soil gas pressure. That's not always easy to do, and it's not always that effective. And then there's something called sub-slab depressurization. So we're going to hook up tubing to the area under the floor slab, put a pump on it, and use that pump to remove air from under the floor slab continuously. That'll have the radon flow preferentially to where the air is being removed from under the floor before it can get into the building. So if we have a radon concentration coming at least partially from soil gas, these are some things that we can do for that. The other thing we can do for preventing radon getting into the building is to, number one, reduce our unnecessary water entry. This is actually something that's done a lot in uranium mines, where the water is up close and personal with uranium close by. If that water flows into the mine, that's a really easy way for the air to get radon. So they do what they can to prevent the groundwater from getting into the mine, and that will work as well if we have elevated levels of radon in our water and we can reduce the amount of water that we're using. we can reduce the radon concentrations in our building. That isn't always possible. Another option is to aerate our water prior to entry. So if we have the water agitated in the presence of air before it comes into the building, a lot of the radon will come out of the water before it gets in, which means that it's then not going to come out into the air, into the facility. Finally, once it's in the facility, we want to see what we can do to prevent radon getting into the workplace air. So when we have water that's bringing in radon, we want to limit the aeration of that water inside the facility. We want to reduce our agitation, splashing, that sort of thing. If we have to spray, we should use radon-reduced water for the spraying, because that active spraying will really help that radon get into the air if it's in the water. If we do need to do aeration, we need to add oxygen for the process that we're using the water for, we should do that aeration in a place separate from the workplace air. So we would have our aeration columns, for example, outside or in a separate room with separate ventilation. Finally, we could look at separating our breathing air from air near agitated water. So for example, if we have a wastewater channel where air is bubbling over the floor as it's draining from the facility, if we put covers on those to keep the air around that water from mixing with the air that we breathe, we're going to prevent radon getting into higher concentrations in our air that we're breathing. So here's an example of the water aeration prevention. So in our before picture, we had water that would just drop 2 or 3 feet down into the wastewater channel, and it was freely mixing with air there and would easily allow radon to get into the air. After a pipe was put on to bring the water directly down into the water in the bottom of the wastewater channel, there's much less mixing. The radon doesn't have the opportunity to come out of the water that's falling and get into the air that then is in the facility. The addition of a cover over this channel as well will prevent the air that does have radon come out of it into it from the flow of the water from getting into where the workers are working. We can also use ventilation, so we can remove air at our water aeration point or where the water is disturbed prior to that air becoming to the point where people are breathing it. We already mentioned separating the ventilation for our indoor aeration chambers. If we cannot prevent aeration and disturbance, see what we can do to prevent the air there from coming into the area we're breathing. So for our wastewater channel that we cover, maybe we put an exhaust fan to blow it directly outside from the channel, and therefore our air is going to flow into the channel rather than out of the channel. We can control our temperatures to some extent. Cooler air will take up less radon than warmer air. So by cooling our facility, we're going to reduce our radon concentrations in the air somewhat. And then we can also look at controlling our airflow path. We may want to make sure that the air is flowing from our low-risk areas to our high-risk radon areas rather than the other way around. So if we have, say, a wastewater channel, and air can flow through that from a high water use area to a low water use area, maybe we want to put some sort of barrier in that channel to prevent the air from flowing from the high water use area to the low water use area. Studies have shown that aeration and ventilation independently are not always sufficient. Often the two have to be combined for effective radon control in high water use facilities. So we're not always going to be able to solve it with ventilation. We're not always going to be able to solve it with aeration. Sometimes we have to do both in order to keep our radon levels low. If we are unsuccessful at bringing radon levels down and we can't prevent that radon from getting into the air, we may need to use protective equipment, personal protective equipment. And the type of equipment that we would use for this would be a properly fitted particulate respirator. Remember, the radon progeny is a particulate that's attaching to the dust in the air. The properly fitted particulate respirator is going to prevent those particles from being breathed into the lung, therefore preventing the radon progeny from being inhaled, and that will reduce the dose. Respirator protection programs can be expensive, difficult to maintain. We also have to make sure that we have properly fitted respirators. A respirator that's poorly fitting, you might not even bother wearing. So this is generally considered to be the last choice. We should do everything that we can to keep our elevated radon levels, bring our elevated radons down before we introduce protection equipment. But in some places we may now have no choice, right? Our aeration facilities where we are aerating the water and radon is therefore being driven off will have elevated levels compared to other areas. And if we have to do maintenance in those areas and things like that to spend any time, a particulate respirator is certainly of use to help reduce dose if necessary. When we're controlling our radon hazards, another thing employers need to do is make sure that their workers are aware of what the hazards are. So let the workers know that elevated radon does exist in the area and what those levels are. A good way to keep doses down is to put protocols in place that limit our time in areas with elevated radon areas. So if we don't have to do something in our high radon area, we can take our broken piece of equipment and fix it somewhere else, then that sort of procedure and protocol can be put in place. And once those procedures are in place under health and safety regulations, employees are also have responsibilities, and they're required to follow the procedures and protocols that are provided by the employer. Really, the only way to know how much radon we have in a workplace or in our home is to test it. So I want you to keep in mind that we can't know otherwise. We can't smell it, see it, taste it, feel it. The only way to know if radon is there is to test. When we're testing, we should use a long-term test. 3 to 12 months is typically recommended for homes. In higher workplace environments, high-risk workplace environments where a lot of groundwater is being used, perhaps start with a shorter term of that, maybe do a 2 or 3 month test to see what levels you're at. Last thing you'd want to do is test for 12 months and find out your levels are above what the detector can detect. Once we've determined whether or not we have radon present, now we want to look at what our average annual concentration is. So we may do a 3-month test and then another 3-month test and then another, do a continuous series of 3-month tests so that we've had 4 over the year, and we can take the average of those 3-month tests to figure out what our average annual concentration is. We can then compare that to the Canadian norm guidelines, figure out what we have to do, what level are we at, are we in the uncontrolled category? Are we in the norm management category? What now is our obligation to do for workers? So thank you very much for joining us for the webinar. So if you want more information, here's our website, so radiationsafety.ca. We have a 1-800 number. If people have questions, they can call to speak to one of our scientists. If somebody isn't available immediately or we don't know the answer to the question, we'll certainly look it up and call you back. And we also have our email, so info@radiationsafety.ca. All right, and we can go a little bit past 3:30 if people want. We have questions that can be answered. So I see a few people have typed in a couple of questions. If you have any other questions, please don't hesitate to type a question into your question section. And let me see if I can figure out how to put my webinar web camera back on to answer the questions. That's not it. There it is. There we go. We've got the webinar web camera back on. So a couple of questions have been typed in. Oh, a suggestion for the poll. So thank you, Craig, and consulting for where people work. That's awesome. I like that idea. I'll have to remember that for next time. Somebody has asked where we can obtain information on how temperature, humidity, barometric pressure affect radon levels, or is it just a general statement? It is, for now, just a general statement. There might be, I will look and see if I can find for you any clear documentation as to what's there. Temperature, for sure. The higher the temperature of the air, the easier it is for the radon to come out of the water into the air. More humid air can hold more radon. I don't know if we have anything for radon that's equivalent to a Henry curve. I would assume so, but don't have it at my fingertips, so I will certainly look that. Another question was, can radon gas cross from a gas to the blood side in the lungs, such as oxygen does? Well, radon is actually soluble in water, so theoretically you could have some radon rejoin the water state or dissolve into the water in the lungs and become into the bloodstream. It's not our typical hazard that we would expect from radon. So therefore, really the concern from radon gas is the radon progeny that we breathe in as particulates. Next comment is about pregnancy. So the question, continuing the previous one, would it be because the fetus is fed by the bloodstream that the limit is there? Well, the Canadian Norm Guidelines limit for pregnancy is the overall limit for all exposures to radioactive material, naturally occurring radioactive material. So if you are working in an area where you are, I don't know, mining something other than uranium, and there's some uranium present, that naturally occurring radioactive material that's present in that job site would potentially cause a dose. So the pregnancy limit actually applies to all naturally occurring radioactive material use in industry other than the nuclear industry. Really, the pregnancy limit is not going to apply to radon because radon is a lung hazard. It's not a hazard for the rest of the body. Okay, according to the next question, according to Health Canada, there are no guidelines for radon gas in drinking water. Yes, that's definitely true. Wouldn't agitation still occur inside of us and still release radon progeny? Well, the concern with radon in water and agitation is the agitation of radon in the presence of air. So when we have water spraying or water bubbling over a floor, that agitation in air actually allows the radon out of the water and into the air. And then once the radon is in the air, it decays to radon progeny, which we breathe in. If we ingest radon-bearing water, that radon is a gas. So theoretically, if that gets to the lungs, it can come out of the water phase and become a gas in your lungs, but then you're just going to breathe it out. So it's really not a hazard from ingestion. It really is only the hazard when we breathe the radon progeny. Next question is from a former nuclear energy worker who was used to working in millirem, and they're asking how does that equate to millisievert? Well, millirem and millisievert are measuring the same thing, kind of like inches and centimeters, so there's actually a very easy conversion. 1 millisievert is equal to 100 millirem. So 1 millisievert of dose is equal to a limit of 100 millirem. Next question was asking if we would share a presentation, or at least a PDF. It's great. Thank you very much. Yes, you can actually download the presentation right now from the handout section of the webinar page. We will also be posting it on our website, and we'll let people know once it's posted and available to get from the website as well. Daryl is asking if there's a plan to further lower the limit from 200 to 100 becquerels per cubic meter. I'm not aware of any plan in Canada right now to lower the limit from 200 becquerels per cubic meter to 100. In other places in the world, there are lower levels. World Health Organization, I think, recommends either 100 or 150. I get their number mixed up in my head sometimes. There are definitely places around the world who have limits of 150 and 100. I'm not aware of Canada planning to lower the limit anytime soon. Okay. Somebody's asking about radon tests. So radon tests are available in stores like Home Depot. Are they effective? They can be. But you have to be careful the type you're buying. So in stores like Home Depot, you can buy a radon test kit. You can buy both long-term test kits there and short-term test kits there. So what I would recommend is that if you are buying a test in Home Depot, that you make sure that you're buying a long-term test kit, one that you're going to deploy for 3 months or more. You don't want to get the short-term ones. They're not as effective, and depending on the shipping times, they can be completely ineffective because by the time they get to where they're going, there's no radon left by the time they get to the analysis lab. With this type of test, I have heard problems about people not getting results. So a lot of them are mailed to the States. Be careful if you use that type of test to make sure that you are putting in the appropriate postage to make them get there. If you aren't at all sure about that sort of thing, you can buy radon test kits from us from our website, radiationsafety.ca. There's a question: are there any ground materials that emit higher levels of radon than others? I'm not quite sure what you mean by ground materials. So radon comes from the decay of uranium in our soil and in our rock. So the higher the level of uranium that's present, the more radon that will be generated in that location. So if we're looking at one type of rock versus another type of rock, yes, if you have higher concentrations of uranium in that rock, it will generate more radon or emit more radon than the rock that has less uranium in it. So I hope that answers your question. If not, feel free to type a clarification. Okay, so question, can I discuss a little bit about a workplace having an area with more than 200 becquerels per cubic meter, but by tracking staff time in all areas, we maintain doses less than a millisievert? This is a very good point. When you are in the norm management guideline, classification of Health Canada's norm guidelines, so you're between 200 and 800 becquerels per cubic meter. The program that you need to put in place is to control dose to workers. So part of that can be done by limiting time in an area that is known to have high radon concentrations. So let's take a facility that has an indoor radon or an indoor aeration chamber that has high radon levels in that location, and the rest of the facility has lower doses. Let's say for this point lower concentrations below 200. The facility still has to do some control because you have a location that's above 200 becquerels per cubic meter. But if you're measuring your concentration regularly and you know what your long-term concentration is, and you know how long people are exposed to that area, so say you're tracking and you know that it's an hour a week, for example, that people are in there, you can calculate how many hours that worker is exposed to the concentration that you've measured in that area. And using the dose conversion factor in Health Canada's norm guidelines, you can then calculate the dose to the worker. So remember that 200 becquerels per cubic meter over 2,000 hours was a dose of 1.4 millisieverts. So 400 becquerels over the same time frame would be 2.8 millisieverts. If we have an elevated concentration over a shorter period of time, we can then figure out what the dose is to that person. So maybe it's 400 becquerels per cubic meter, but they were only in it for 400 hours. If we do that math and we can say that their exposure is such that their dose is below the public dose limit, so it comes up less than a millisievert, then we can show that we're meeting the requirements of Canada's norm guideline. We're keeping doses below the limit. And even if we can't reduce our radon levels in that high place, like our aeration chamber, we're still able to meet the requirements to protect the workers by monitoring time and radon concentrations. Excuse me, I'm losing my voice here. So I hope that answers your question there. Tim has gotten back to me that so the discussion about ground materials, so he was definitely talking about rock type. Yeah, so granite versus limestone is a good example. Granite would typically have a higher concentration of uranium than limestone, I believe. I'm not a geologist. Granite, marble can have some more. So the type of rock that you're going to find near a uranium mine versus the type of rock that you're going to find in I don't know, where's a good place? Why is the name of that place not coming to me? Sorry, it was a bit of a crazy day. So I think I'm going to refer you to a geologist as to which type of rock tends to have more than others, but granite definitely can have more uranium than others. So you're going to have the potential for more radon in areas with lots of granite, like the Canadian Shield, versus places with limestone that wouldn't have as much uranium present. Somebody's asked about the accuracy of the Serantium electronic monitor. I'm afraid that one I'm not familiar with. It's something we can, maybe you mean the Corentium electronic monitor. Excuse me, that's something we can take offline and discuss. At the moment, there are only a few electronic monitors listed by the Canadian Radon Proficiency Program, or Canadian National Radon Proficiency Program. I believe the Corentium electronic monitor is one of them. We have not done a lot of testing ourselves about how accurate various electronic monitors are. We actually now, the Radiation Safety Institute has a certified radon chamber. So this is something that we can do now. So if you're not sure, if you have an electronic monitor, this type or another type, we can now calibrate them. So you'd send them to us. We would put them in our chamber with a known radon concentration and tell you how close your measurement was to what we were actually exposing it to. So we can certainly look at that, but we haven't done it up until now for a lot of it. Jane has said that radon is killing 3,200 Canadians per year and is less reported than that by road and terrorism. That's perfectly true. We have the potential, and Health Canada's estimates are that approximately 3,000 people die from lung cancer per year because of radon exposure. A lot more lung cancers are from smoking, but it's certainly a possibility. Could there be some more awareness that good documentation available somewhere, and who would be held responsible, so the general public and worker? Well, Health Canada is doing their best to try and get the issue of radon across to people. So November is Radon Action Month. In November, Health Canada and the Institute and some others, the Lung Association, generally put out a media campaign to make people aware. We're getting there. More people are becoming more aware of radon. And that's one of the reasons why we do this type of webinar and presentation, is to help promote awareness of this hazard. So at the moment, though, it's Health Canada is doing the best they can to make sure Canadians are aware. It's getting better. It's certainly not there yet. Okay. All right. So Jason here is talking about the Ontario Building Code. So the Ontario Building Code outlines that harmful vapor intrusion be addressed if identified. When do I think that this will be actively enforced by municipalities? Well, at the moment, as I think you're aware, there are 3 municipalities in Ontario that are addressing it because they have had elevated radon levels. Elliott Lake is a good example. There used to be uranium mines in Elliott Lake. It's a high uranium risk area, so they've noticed higher elevated radon levels. So they have their own local building code where radon prevention measures must be installed when houses are built. BC also implemented this in areas of their interior, that homes have to have radon prevention and radon mitigation pre-installed when they're built now. So it is in the Canada Building Code as a recommendation. I don't know whether or when municipalities or provinces will enforce it. I agree, it does seem like a big liability concern. I know some of the home builders are concerned about it. In Ontario, there's now what's called the Tarion Home Warranty Program, actually warrants against radon. So if a elevated radon is noticed in a home after it's built within the time frame of the warranty, which I believe is 7 years, the warranty will cover the remediation costs. So it is potentially an issue for sure. It's something that we're hoping the awareness gets out so people are aware of. We have a geologist online. So he says carbonatites and uranium-bearing minerals. Yeah, I don't know where you would find these carbonatites and uranium-bearing minerals. There generally are, yes, associated with the highest radon concentrations in buildings. So if we look at Winnipeg, Winnipeg is in an area with a higher uranium-bearing concentration in their rock, and we see elevated radon in those areas. So generally speaking, the more uranium that you have in the rock around your home and business, higher the potential for radon in your home. It's not the only way that we get radon in homes, though. Health Canada has done or businesses. Health Canada has done a cross-country survey, even in areas that don't have the high radon-bearing rock, high uranium bearing rock, you'll still see some places that have elevated radon. So really we recommend that people test wherever they are. New Brunswick has the highest radon level. Is there a guideline for workers in this province? I'm not sure it's actually the highest radon levels. I think it can be one of the higher ones. I would have to double check what New Brunswick's health and safety regulations are and get back to you. So Jean, if you want to get in touch with me afterwards, my email is lboksman@radiationsafety.ca, or just email at info and ask to have it forwarded to me, and we can take that offline and help you figure that out. There's someone who's also CMHC, Canadian Morgan Housing Company. Should they make radon measurements mandatory, as seems to be the case for water organic tests? That's a very good question, and I'm not sure where they're going to go with that. In the U.S., there are certain provinces, certain states that require a radon test be done as part of a home sale. I believe Quebec and Ontario is heading that way if they haven't fully implemented it. I would like to see it as part of the home sale process. When you're selling a home, the buyer has a chance to do a radon measurement, and part of the sales will cover the radon mitigation if needed. I don't know that Canada will get there across the country. Maybe certain provinces will recognize it as an issue and implement it locally. It'll be good to see what happens. All right, we're about 10 minutes over time. I think we'll close the webinar now. I want to say thank you for everyone for joining us today. We will send you an email and let you know when the website has the slides as well as the recording from the webinar. And thank you all for joining. Have a wonderful rest of the day.